Driving is hard. I know we've all been in the position where you end up on the other side of the road and only realize it when you reach a four-way intersection. Right, guys? Anyway, Virginia is no stranger to traffic regulation problems. According to the Virginia Department of Transportation, the past 5 years in Virginia have seen an average of about 120,000 crashes and 900 fatalities. That is 900 fatalities too many. Feeling inspired, we set out to use machine learning techniques to help create a safer Virginia by identifying issues with road regulation and unsafe driving practices. The Kaggle dataset we found consisted of over 2 million total data points on car crashes from 2008 to 2024, with over 5 dozen features detailing crash characteristics such as degree of injury, factors leading to the crash, location, and more. We custom tailored each model we built to leave out repeated or unnecessary features, and we also use simple imputing and one-hot encoding to prepare our data.
Once the data was fully cleaned up, we started with using k-means clustering to analyze the data. It's widely used and straightforward, and also typically produces great models from complex datasets. As a trial run, we chose to do k equals 4 clusters to see what would happen. However, as you can tell from the map, the main feature being split on is the type of roadway, like highway versus rural roads, which isn't very informative for crash severity. To improve our clustering, we tested k values between 2 and 20, and identified the elbow at k equals 13. This resulted in the following chart, which we overlaid over a map of Virginia. There is still a geographic component, but we can now look at each centroid to determine what typically defined each cluster. We tried to do an ANOVA test to determine feature importance, but since our dataset was so large, there were very low p-values for every numerical feature, suggesting that they were all extremely significant. Instead, we decided to look at the means of each cluster for further insights. For example, Cluster 9 was likely formed based on accidents that had one or more people killed, and it also had the second highest average speed above the limit out of any of the clusters at 19 miles per hour, demonstrating a correlation between speed limit violation and people being killed. That makes sense, but we were also able to draw some less obvious connections. In the cluster with the highest average deaths, about half of people involved were not wearing seatbelts, while in all the other clusters, over 95% of people were. Roads with steep slopes were also overrepresented in the deadliest cluster, as were two-way undivided roads, leading to the conclusion that undivided roads leave more opportunity for head-on collisions.
Next, we tried classification. We first trained a 5-class random forest model based on the severity of damage to people and property, ranging from only property damage to at least one fatality occurring. Sadly, this model took 12 hours to train and only achieved about 60% accuracy, so we switched to a binary classification model by merging the 5 classes into 2 as shown here. Our goal was basically to identify whether a crash was severe enough to send anyone to the hospital or not. We also switched from using random forest to XGBoost, which mixes ensemble learning with base decision tree models to strengthen predictions and prevent overfitting. After this, we trained a couple of models that focus on finding links between specific features from the dataset and crash severity, using Shapley additive explanations, or SHAP, to calculate feature importance and make conclusions. For example, one model showed us that well-maintained double yellow lines were more likely to result in non-serious crashes based on traffic control measures and road condition. Another model showed that dirty or sandy roads combined with misty conditions were likely to cause serious accidents based on roadway surface and weather conditions. However, by far the most useful model we trained only included features related to physical jurisdictions throughout Virginia and led to the identification of trouble areas such as Franklin County and Manassas Park, and good areas such as Vinton and Warrenton. These were identified by analyzing each jurisdiction's SHAP scores and noting down polar values.
Our results gave us a great starting point for identifying issues with driving regulations and conditions. For example, by researching the trouble areas, we found that Franklin County has a lot of narrow, rural roads with sharp turns and low lighting, and that both Manassas Park and Blacksburg have high pedestrian injury rates because of unsafe pedestrian crossings. Researching the good areas showed us how using speed tables or raised crosswalks can improve pedestrian safety, like in Danville. This data can be combined with the clustering results to lobby local governments throughout the state for more funding for road safety measures like the ones mentioned above, and also for better drivers' education and awareness programs to encourage safer practices like keeping seatbelts buckled and knowing how to drive in a variety of different and difficult conditions. Thank you for watching our video, and we hope you found our research interesting.